Labguy here. Today we're going to do a deep dive into the Cartrivision instant replay television camera circuits. This is for your benefit so that in the next video, when we go to repair serial number 7, you folks will have an idea of what's going on inside the camera in general, at the least. So without further ado, let's get on with the deep dive. The heart of a VIDICON camera is the VIDICON tube, of course. Here we see the schematic diagram and a mechanical diagram of a typical VIDICON tube. A VIDICON is a vacuum tube that is very similar to a picture tube or a cathode ray tube. It is a cathode ray tube that picks up light rather than emits light. Starting on the left side, we see that there is an element called the target. The image from the lens is focused on this end of the tube. At the opposite end of the tube is a heater and cathode, which is a source of electrons, an accelerating grid, grid number 2, which speeds those electrons towards the target, 2 more electrodes, grid number 3 and grid number 4, which are responsible for shaping the electron beam and making the electron beam arrive parallel to the face of the tube to form a round spot. The photoelectrode is called the target. When light strikes the photoconductor, it changes its electrical resistance. If there's a bright spot, more current flows out of the target connection, and if there's less light, then less current flows from that connection. That is how the image signal is generated as the electron beam spot is systematically swept over the imaging area by the horizontal and vertical deflection coils, and it is kept traveling in a straight line parallel to the axis of the tube by the action of the focusing coil. On the extreme right side of this diagram, we see the schematic symbol of the same tube. You can see the typical voltages for the elements. The heating element operates at 6.2 to 6.3 volts. The cathode in this camera is switched from 0 volts beam on to plus 18 volts beam off. This is how they blank the beam during retrace so that you don't end up with streaks in the video signal. Grid number 1, G1, is held at a minus 40 volts. This controls the amount of electrons reaching the target. Grid number 2 is the accelerator, and it is operated at plus 300 volts above ground. The focus electrode is operated at a lower voltage of plus 200 volts, and the screen grid at the front of the tube, they call a decelerator in the mechanical image, is operated at 300 volts. This creates a differential field between the grid number 2, grid number 4, and grid number 3, which acts like an optical lens to focus the beam from the aperture in grid number 1 to form a tiny spot on the photo target for sampling the points as it sweeps back and forth. And that is how a VIDICON tube works. The following circuit descriptions are derived from the service manual for this camera. We could go through the original schematic of the Cartrivision camera, but as you can see here, it's a bit convoluted. Oh, my mistake. Here's the correct schematic. You can see that it's a very busy schematic that I call a spaghetti schematic. So I've taken the liberty of redrafting this schematic into a CAD program called Kicad and putting it on 2 pages. The first page contains the video amplifiers, the vertical deflection, the focus stabilizer, and the 11.2 volt voltage regulator. The second page contains the master timing sync generator, its clock oscillator, its phase lock circuit to lock it to the AC power line, the beam blanking circuit, the horizontal deflection, and the high voltage power supply sections. So this will make it easier for us to go through each individual circuit. The camera electronics are completely contained on two printed circuit boards mounted on each side of the camera above the deflection unit. The video board, board number 1, on the right side of the camera contains the following circuits. 1. Regulated power supply. 2. Video amplifier and automatic light control, ALC. 3. Sync pulse mixer. 4. Vertical deflection generator. 5. Focus current stabilizer. The pulse unit, board number 2, mounted on the left side of the camera contains the following. 1. Voltage controlled oscillator. 2. Divide by 2 digital frequency divider. 3. Divide by 525 digital frequency divider. 4. Digital phase comparator. 5. High voltage power supply. 6. Horizontal deflection generator. 7. Blanking pulse mixer. The two boards are attached by means of plug-in connectors, allowing removal for its parts replacement. Troubleshooting is most easily done with the PC boards in place using the board layout diagrams. Video board, board number 1. 1. Regulated power supply. The supply voltage from the VTR is plus 18 volts. This voltage is processed into a stable, regulated plus 11.2 volt supply for the camera circuitry. The plus 18 volts is used directly for the blanking generator to develop the 16 volts needed for blanking the VIDICON during retrace. Q112 is used as a series pass transistor with plus 18 volts applied to the collector and the emitter supplying the regulated 11.2 volts. The base current for Q112 is supplied by driver transistor Q111. The base drive for Q111 is in turn supplied by Q110. The emitter of Q110 is held at 5.6 volts by the Zener diode D101. The current for D101 is supplied by R122. R130 is adjusted so that the conduction of Q112 produces 11.2 volts at the emitter. Any increase in the voltage at the 11.2 volt line would cause an increase in the conduction of Q110. This would decrease the collector voltage, which in turn decreases drive to Q111 and Q110. This action lowers the voltage at the 11.2 line, thus maintaining a constant 11.2 volts at the emitter of Q110. A decrease in the 11.2 volt line produces a similar but opposite effect. The supply voltage for the ICs is derived by series connecting the VIDICON heater with the ICs. The ICs require nominal plus 5 volts for power, 4.75 volts to 5.25 volts. If needed, R122 is connected in parallel with the VIDICON to increase the supply voltage and in parallel with the IC supply to decrease the IC supply voltage. Video board, board number 1, part 2. Video amplifier and automatic light control, ALC. The video signal from the target terminal of the VIDICON is applied to the gate of field effect transistor Q102. The video is further amplified by Q103 and Q104 to achieve 1 volt peak to peak at the output. The input impedance of the field effect transistor is approximately 200,000 ohms shunted by 10 picofarads due to negative feedback from the output through C106 and R111 to the source pin of Q102. Frequency compensation is adjusted by R112 and R116. These controls are adjusted for minimum trailing edges after a sharp transition from black to white or white to black. The coil in the collector circuit of Q104 provides high frequency peaking to compensate for the finite diameter of the VIDICON scanning beam. Frequency response should be above 2 MHz. Blanking level is inserted with Q105. The blanking signal is obtained from blanker Q201. The sync is inserted at the emitter of Q105 from Q108 and Q109. The sync amplitude is adjusted with R118. The automatic light control circuit compensates for varying light levels by stabilizing the current supplied to the VIDICON target. Q101 acts as a constant current source supplying approximately 150 nanoamps, 0.15 microamps, to the VIDICON target. Video board, board number 1, part 3, sync pulse mixer. Transistors Q108 and Q109 act as switches that insert the sync pulses into the video during blanking time. Q108 saturates when a pulse occurs at the base, producing the vertical sync pulse. The pulse width is determined by C123, R125, and R142. The pulse width should be 3 to 5 horizontal lines. Q109 injects the horizontal sync pulse in a similar manner. The flyback pulse from the yoke is applied to Q109, producing the 5 microsecond horizontal sync pulse. Video board, board number 1, part 4, vertical deflection generator. The vertical scanning sawtooth is developed by charging capacitors C121 and C122 through R141. This is basically a ramp generator that produces the trace portion of the vertical sweep. The retrace portion is produced as Q115 is switched on, discharging the capacitors and restarting the sweep. Note that the sweep system is not an oscillator, but a ramp generator and requires a reset pulse to operate. This pulse is derived from the IC dividers. The amplitude of the sawtooth is adjusted with R138, while R139 and R140 adjust linearity. Q114 is the driver for the Class A output stage Q113. The sawtooth is coupled to the yoke with C120. R135 adjusts the centering by controlling the DC current through the yoke. Video board, board number 1, part 5. Focus current stabilizer. Focus current is established by the voltage drop across the emitter resistor of Q118. The voltage at the emitter of Q118 is determined primarily by the base voltage of Q116. This is because Q116 acts as an emitter follower, thus establishing the emitter voltage of Q117. Conduction, or more correctly, non-conduction of Q117 allows Q118 to supply current to the focus coil. The differential transistors of Q116 and Q117 have a great deal of immunity to changes in power supply voltage, and the 100% negative feedback of Q117 and Q118 afford excellent temperature stability. As Q118 tends to conduct more, the emitter voltage would drop. This would forward bias Q117, which would in turn decrease the bias on Q118, bringing the conduction back to the original level. The transistors in effect provide a very stable, constant current supply. Any change in the resistance of the focus coil also has virtually no effect on the current through the coil. R145 is used to set the focus current. Pulse unit, board number 2. Part 1. Voltage controlled oscillator. All sync frequencies used in the camera are derived from a 31.5 kHz voltage controlled oscillator. The oscillator is basically an astable multivibrator with an AFC voltage applied. The AFC voltage applied to Q205 maintains sync with the 60 Hz power line. R206 adjusts the frequency of the master oscillator. Q206 converts the 31.5 kHz signal to the logic levels needed to drive the IC frequency dividers. A divide by 2 circuit is used to develop horizontal sync, and a divide by 525 is used to develop vertical sync. Pulse unit, board number 2, part 2. Divide by 2 digital frequency divider. IC214 contains 2 identical JK flip-flops. One is used as a divide by 2 and the other is used as a phase comparator. The divide by 2 portion of IC214 has 31.5 kHz applied to the clock input pin 5. The output at 15,750 Hz is taken from the Q output pin 9. This output is used to drive the horizontal deflection circuit. Pulse unit, board number 2, part 3. Divide by 525 digital frequency divider. The divide by 525 circuit is actually composed of a divide by 5, divide by 5, divide by 3, and divide by 7. 5 times 5 times 3 times 7 equals 525. Notice that these factors are prime numbers. This is 525 factored. IC211, IC212, and IC213 each contain separate divide by 5 and divide by 2 circuits. IC211 is used to divide by 5 and the output is applied to IC212, which again divides by 5. The divide by 2 flip-flops in IC211 and IC212 are interconnected to form a divide by 3 counter. The output is applied to IC213, which is connected to form a divide by 7 counter. The output from the last flip-flop will be 60 Hz, 31.5 kHz, divided by 525 equals 60 Hz. It is necessary to develop the horizontal and vertical frequencies from the same master oscillator to provide interlace. Pulse unit, board number 2, part 4. Digital phase comparator. A 60 Hz positive half-wave signal from the VTR power supply is applied to Q207's base. The output at the collector is a negative going pulse that is in sync with the 60 Hz power line frequency. One of the flip-flops in IC214 is used as a phase comparator to ensure that the camera output remains locked to the line frequency. The 60 Hz output from the 525 divider is applied to the reset pin 2 of the flip-flop. This pulse sets the output Q to low. The pulse from Q207 line frequency is applied to the clock terminal of the flip-flop pin 1. The Q output, pin 12, switches to a high at the negative edge of this clock pulse. Q remains high until it is reset by the next pulse from the IC dividers. The output is a series of pulses at 60 Hz whose width represents the phase difference between the IC divider output and the 60 Hz line frequency. R206 in the master oscillator is adjusted for a duty cycle of 1:1. This output of approximately 8.3 milliseconds high and 8.3 milliseconds low ensures the proper AFC range. AFC is automatic frequency control. Pulse unit, board number 2, part 5. High voltage power supply. The high voltages necessary for the operation of the VIDICON are produced in a manner similar to the horizontal sections of a TV set. The 15,750 Hz square wave from the IC divider is differentiated and applies to Q209, which amplifies the pulse and drives Q208. The transformer in the collector of Q208 supplies the pulses necessary to drive the horizontal deflection transistor Q10, the blanking transistor Q202, the 75 volt negative supply diode D202, and the 300 volt positive supply diode D203. Diode D204 acts as a damper for the transformer. Pulse unit, board number 2, part 6. Horizontal deflection generator. The horizontal deflection circuit is similar to the system used in a TV receiver, except that the circuit has no oscillator. When voltage is applied to the yoke, a linear current results because of yoke inductance. Q210 acts as a switch that is on, saturated, during sweep time. A negative pulse is applied to the base of Q210 from a winding on T201, turning it off. When Q210 turns off, the yoke and C218 form a resonant circuit. The collapsing field of the yoke charges C218, and the C218 discharges back into the yoke. Further oscillation is prevented because damper diode D205 conducts at this point and forces the yoke current to decay linearly. The cycle is repeated each time a reset pulse is received from the IC divider. The yoke is AC coupled by C219. Width adjustment is provided by the horizontal amplitude control R234. Pulse unit, board number 2, part 7, blanking pulse mixer. A pulse from the 525 divider is differentiated by C202 and R206 to provide a vertical blanking pulse of approximately 1 millisecond. A negative going pulse appears at the collector of Q203. A positive pulse from the high voltage transformer is applied to the base of Q202, providing a horizontal blanking pulse of approximately 11 microseconds at the collector. The blanking signals are mixed at the collectors of Q202 and Q203. This negative going composite blanking signal is applied to PNP transistor Q201. The supply voltage for Q201 is the plus 18 volt supply, since the regulated 11.2 volts would not provide a pulse of sufficient amplitude to ensure blanking of the VIDICON tube. The blanking signal is also applied to the video mixer transistor Q105 in the video channel. Now, wasn't that exciting, boys and girls? I hope you enjoyed Labguy's dramatic reading of the Cartrivision VIDICON camera service manual, theory of operation. You may have noticed several errors in the dialogue. Those were written right into the service manual, and I read the service manual before I produced all of the graphic slides. The production of those slides is one of the reasons this video has taken so long to put out. That, and I now have a full-time day job. So that really surprised me at how many luxurious hours I had to myself every day. But that's okay. Those luxurious hours don't pay the bills. The job pays the bills. And it's going okay. Thanks for asking. In the next video, I will endeavor to repair VIDICON camera number 7. As you recall, we tested all 7 cameras. 6 of them are functional. Some of them very well. Some of them need adjustment. They all need adjustment. So we'll get to those as well. In the next video, I hope to repair camera 7 for you, and we'll go through that. This video should have prepared you folks for that repair-a-thon when we get to that. I'd like to welcome all of the new subscribers, and greetings to all of the old subscribers. As you know, you guys rock. You have good taste in video channels, especially the simpler ones like this. I'm not here to impress you with my production skills. I'm here to tell you about things that your grandpa used, and to show you that not everything that's old is necessarily bad. So, with that, until next time, Labguy out.